Have you ever just stared at a pot of water about to boil and thought, how does it do that? It seems so simple, but it's actually one of the deepest, most fundamental questions in physics, and today we're going to pull that thread.
I mean, think about it. At sea level, water always boils at exactly 100 degrees Celsius. Not 99.8, not 102.2, a perfect 100. How do all those water molecules, trillions and trillions of them, all agree at the exact same instant? Okay, time to turn into a gas. How does the universe know to enforce that rule so precisely?
And, this isn't just about water. Every single material, whether it's iron or nitrogen or salt, has these incredibly precise, unchanging rules. We count on this consistency for literally everything. But the why of it all, why these temperatures are so specific, has been a surprisingly stubborn mystery.
Well, a new theory called the First Quanta theory is offering up a really radical, but also beautifully simple answer. It suggests that these phase changes aren't governed by some abstract, invisible law, but by something much more tangible, a kind of inner friction built into the very fabric of matter itself.
This idea is called material drag, and the concept is this. Every single atom in a substance feels a resistance, a drag force, as it vibrates and moves around. But this drag isn't coming from the outside. It's an internal friction created by all the other atoms in that same material. It's like the material itself is resisting its own internal motion.
Let's make that feel a little more real. You know when you stick your hand out of a moving car window and feel the air pushing back? That's drag. Now, just imagine you're a tiny little atom inside a solid block of lead. As you get hotter and start vibrating like crazy, you're feeling the similar kind of drag from all the lead atoms packed in around you. That's material drag.
Okay, so it's a cool idea, right? But in physics, an idea is only as good as its predictions. So here's the ultimate test. If this material drag is real, then could we build a thermodynamics simulation, plug in this one principle, and have it predict the exact melting and boiling points of real-world materials from scratch?
And that's exactly what they did. The process itself is just beautiful logical science. First, you build a 3D computer model of a material's atomic structure, all lined up in a neat crystal. Second, you start injecting heat, which in a simulation just means you tell the atoms to vibrate faster and faster. Third, you track the temperature, and then you just watch. You watch for the precise moment that all that vibration becomes too much, and the perfect crystal lattice just shatters. That's your melting point.
So they ran the simulation. They heated the digital atoms, they let them vibrate, and the computer kept its eye out for that moment of truth. So the big question is, how did it do? Was this First Quanta theory with its core idea of material drag just a nice story? Or does it actually have real predictive power? Well, the results are, honestly, they're stunning. Just look at this table. For something like lead, the simulation predicted its melting point with 99.6% accuracy. And its boiling point? The same. For aluminum, which has a way higher melting point, it's still 99.5% accurate. And it even works for something totally different, like cryogenic nitrogen. I mean, across the board, the predictions from the simulation just nailed it.
Let that sink in. The average accuracy across a whole bunch of different materials was over 99%. The simulation, based on this one single idea of drag, didn't just get it right, it was incredibly precise.
And this chart really drives the point home. This wasn't a fluke. It holds true for heavy metals like lead, lighter metals like aluminum, and even a gas like nitrogen at super low temperatures. When a single principle works this well across such different substances, it's a huge sign that you're onto something truly fundamental about how thermodynamics works. Okay, so predicting phase changes this well is already a massive achievement. But the hallmark of a really great theory in physics is that it unifies things. It should start explaining other phenomena too. So what else can this idea of material drag do? Well, the theory makes another incredibly bold claim. It says that a material's specific heat capacity, that's just the amount of energy you need to raise its temperature by 1 degree, is actually a direct measurement of this internal drag. It makes perfect sense when you think about it. A material with high drag, like water, needs a ton of energy to overcome that friction and get its atoms moving, which is why it has such a high specific heat.
And the connections just keep coming. This one, single concept of drag, also seems to provide a physical mechanism for the specific heat of metals, the ideal efficiency of solar panels, even the stability of atomic nuclei. It could explain why an electric motor loses energy as heat, and get this, It might even shed light on a famous puzzle in particle physics called the anomalous magnetic moment of the muon. It's like this one idea is a thread that runs through thermodynamics, engineering, and maybe even the subatomic world.
So we started with a super simple question about a pot of boiling water, and we've ended up with this one elegant principle, this idea of internal friction, that seems to connect all these huge different fields of science. It really just leaves you with one final provocative thought. If one simple rule explains this much, what else out there is it just waiting to explain?